Good afternoon, everyone. My name is Zavner. I'm working as a technical director at GigaSpaces. I'm responsible for the technical activity in EMEA, Europe, Middle East, and Africa. I'm working there a bit more than 3 years. Usually my role is to oversee the technical account management of the customers, to accompany the leads before they start to work and to test the product, POCs, pilots, and conferences as we have here. In this session, I would like to talk to you about how to run real-time processing and analytics on big data applications. Of course, it also applies to non-big data applications, to relational databases and so on. But the challenge, as we see with our customers, is usually when we work with big data applications to process massive amounts of data. Next slide. Maybe at the meantime, I will tell you a few words about GigaSpaces. GigaSpaces started around at the year of 2000, 2003. We have two main products. One product is Zap, and this is our first product. Zap is an in-memory data grid. This is going to be our major topic for this session. In-memory data grids are usually used for mission-critical applications with massive load that needs low latency. The other product that we have is Cloudify. Cloudify is a cloud orchestrator. This is used to take existing applications, large applications, and to onboard them to the cloud. So usually it can be any cloud and each type of application. As I said, we are going to discuss Zap. So we provide software middleware for deployment management, scaling, mission-critical applications on cloud environments and also, of course, on non-cloud environments. That depends on the vendor. Usually, vendors like e-commerce, healthcare, banking, finance, they are usually a bit less tolerance for cloud, and they are usually working with physical environment on data centers. Startups and small organizations are more going to the cloud. We have more than 500 customers, starting from small startups towards middle business companies and large enterprises, including Bank of America, Kohl's, Goldman Sachs, 888, and others. Okay, so the agenda is going to be, we will going to start with the challenge of real-time analytics today. What exactly is the challenge? What do companies do? Where the challenge is coming from? After that, we are going to discuss in-memory data grids as a possible solution to solve the challenge. And then after that, we are going to see how Zap exactly can solve the challenge for us. Then we are going to discuss some advanced features that Zap provides. The big one of them is the SSD integration. Of course, we have many other solutions like geospatial and others. The SSD is the one that is helping with the challenge of big data. The demo, unfortunately, we cannot show you here because I could not connect my laptop here, but you are more than welcome to come to our booth, and then we can show you a demo of how Zap is working in real time. And use cases, we can see a couple of them. So let's start with today's reality. Companies today, as you know, develop applications that, unlike before, needs to serve applications that are using numerous of sources, multiple clients that can come starting from PCs, laptops, iPhones, tablets, sometimes TVs, and information is flowing to the application from multiple sources, and more people are using it. The demand is becoming a bit more challenging because the management and the marketing demand also to process more data and to analyze more data. So we have both more analyzation and also multiple client sources. So the number of transactions grows exponentially. If you take e-commerce applications, there are plenty of evidence and plenty of statistics that shows that e-commerce applications grow in more than a few 100% in the past few years, the usage of them. People are, for some reason, they like to buy in e-commerce applications, online banking applications, online gaming. Everyone is using those tools online, and for some reason, people are going much less to the retailers at the shops. The tolerance, on the other hand, for system response times reduce significantly. So on one hand, we have much more demand and much more traffic flows to our system, and on the other hand, there is no tolerance for downtime. System needs to be always up, highly available, and we need to serve the data with with milliseconds of latency. So when people discuss real time, they usually refer to milliseconds, sometimes even microseconds. Okay? Then, in order to gain a competitive edge, the organization needs real-time processing of large data sets. And what usually used to be the solution, a tier-based architecture with relational databases as strong as it can be, cannot always solve the problem for us, since we need to store more data than one machine can handle. So we are working with distributed environments, and also distributed environments that are working on disk, that are disk-based, are also not good enough for us because we need to fetch the data very fast, and that can be only from an in-memory solution. So alongside with that challenge, there are of course plenty of other challenges. We are going to discuss these challenges of peak loads, performance, business continuity, TCO reduction, and real-time big data processing. Let's start with this one. The current tier-based, as we said before, cannot meet these challenges. If you look at the chart that we have here, you will see that on the left-hand side, we have the web client, which is where the request starts. It goes to the web tier, then to the business logic tier. We do some processing. Sometimes it involves the messaging tier, then to the database. It can also be multiple databases, all the way back to the business logic. If it's a transaction that involves few requests to the database, so back and forth, and then the response is going back to the client, which creates a high response time and a high latency. Now, let's see the challenges that we discussed and see what exactly is the problem with the tier-based architecture. Let's start with the database one. The database, when it is stored on one box, it can only scale so far. If you put an Oracle or SQL server, which are great databases and are very fast, they are limited to how fast the box they are stored in is. Okay, so if it's a box of 16 cores, 32 cores, it can only go that high. Of course, that also the data is limited by the amount of disk that we have. Then eventually we have the messaging tier, which also can scale only that far if it's not a distributed environment. Okay, and the business logic tier, which sometimes we end up with massive over-provisioning of resources to meet peak loads. If we take, for example, e-commerce websites in the US that we are working with, Kohl's, so they have a story, and we are going to see it in the use cases, that I think it was the year of 2009, Kohl's website completely crashed during Black Friday, or it was Cyber Monday, I can't remember which one of them, but it completely crashed. Now, when such a system crashed during Black Friday, during the holidays times, it creates, besides the loss of millions of dollars for them, it creates a very, very bad reputation. So companies are very sensitive about that, and eventually they end up with costly over-provisioning to avoid such situations. Then the performance challenge. So we have the network bottlenecks. We need to spend time of serialization and TCP that each one of the tiers that we have here needs to pass the data to the next tier and then wait that the data will come back if it's a synchronous request. We have also the data tier bottlenecks, which, since the data is stored on the disk, Oracle, SQL Server, MySQL, also NoSQL DBs such as MongoDB, Cassandra, Hadoop, the data is mostly stored on the disk. And to go and fetch the data from the disk is very costly in terms of times. I think that Facebook said it once that they found out that RAM request for the memory from the RAM is approximately 100 to 1,000 times faster than request from the disk. Business continuity challenges. If we have the tier-based architecture, which involves the web tier, web server, business logic tier, it can be WebLogic or any other great tool for application server, messaging tier, data tier, and maybe a cache like Redis or Memcached. Each one of these tiers needs to be monitored, needs to be managed by some experts that usually specialize in those specific areas. So eventually, we have too many moving parts. And when we have too many moving parts, we have many costs for each one of them. So applications becomes more error-prone and more harder to troubleshoot. The TCO reduction is also another side effect of that. We need to have experts for each one of them that cost a lot of money. So having many moving parts means higher operational cost, purchase licenses of the application, update, maintenance, and sometimes another application that will manage all of them, monitoring tools that can manage all of them, and everything sums up to higher costs. And another one is the real-time business insights challenges, that this is something that grew up much more in the past few years when, since applications are growing so much, marketing, they have their own demands, their own info that they need to gather from the application. How many transactions do we have? How many transactions did we have in the past month? And compare it to the past month in the last year. And other complex calculations that we need to run on our system that is already pretty heavy with calculations. So we need to be able to provide with info about what's going on in our clusters and in our application to our marketing in order to remain competitive with other organizations. So tier-based architecture cannot solve today's data application processing issues simply because it involves too many tiers. And of course, we are not saying that we need to put everything in one tier, but what we do need to do is to try to see where we can save time and put, for example, the data with the business logic co-located, how we can make our monitoring more efficient, where we can, of course, save also some costs. And this is exactly why we are going to see what in-memory data grids can provide us. So obviously, ZAP can meet all these challenges. There are plenty of other data grids out there. ZAP is one of them. Best to my knowledge, ZAP, Coherence, and Gemfire are the leaders in the in-memory data grid. As I said, there are also other in-memory data grids. Usually where companies are going to take in-memory data grids to production, they want to see some receipts. They want to see some working environments in production using those data grids. So ZAP, as I said, have plenty of them. Now, let's see how ZAP exactly is solving that. ZAP scales the data tier, first of all, using its in-memory data grid, so you can access your data in real time. So if you look at the right part of it, the data tier bottlenecks, ZAP takes it, put everything in memory on multiple machines, on an active application server that we call it a processing unit. And since everything is partitioned and co-located in the memory, so the application, when it fetches the data using SQL, indexes, and proprietary API is available as well. So it will fetch it from ZAP, which will request it from the in-memory. Now, the data tier that we also have now, it can be MongoDB, it can be Oracle, it doesn't matter what. It doesn't mean that it goes away and we don't use it anymore. It just goes to the back, and when we do some operations on ZAP, ZAP will asynchronously persist it to the data tier, so other applications that use this data can continue using it. Also, in case of disaster recovery, which of course ZAP provides the one gateway solution, but in case of disaster recovery within that site or with other sites, we want to have the data persistent, and this is why we want to keep our database just in case. So as we said, we partition the data and store it in memory. So for example, if we have a billion employees that we want to store, and we have, for example, 5 machines, so Zap will partition these billions employees, so each machine will get its own portion, and it has a highly available backup. So we have primary partitions and backup partitions, and the data is stored on these partitions. So instead of fetching, let's say that now we want to get employee number 50, instead of going to the same machine, all of the clients, Zap will partition it, will route it to the appropriate machine. Very same thing like MongoDB and Cassandra are doing, just the difference is that it's fetching it from the in-memory data. The database, as we said, goes to the background. When we start the cluster pulls the data that we want, or all the data from the persistent storage. It can be SSD, it can be MongoDB or other databases, and then it stores the data in memory, index it, so a request usually will take a few microseconds, or if it's a very, very complex calculation, maybe a few milliseconds. Same things goes to the messaging tier. So if we want to understand what benefit we got by putting the data in memory, the main benefit was that we don't need to spend time to go to the disk and fetch the data, which is a huge advantage. But another thing that we can benefit from is if we put also the business logic and the messaging also together with the data. So at the current phase, if we don't put it, so we still have the business logic tier that need to fetch the data from Zap, spend time on serialization and TCP/IP, move it to the application server, process it, send it back, and back and forth, back and forth. If we can put also the business logic together with the data, so then we don't need to spend time on serialization. Everything is running co-located. So eventually, the processing will be very fast. For example, if we take an e-commerce business logic, let's say that a customer wants to make a reservation, to make a purchase now. There are plenty of processing stuff that we do once the placement, once the customer has made the order. It can be billing, shipping, the transaction, the funds, inventory, plenty of stuff that we need to update. If all of these stuff are going to be done when the business logic is co-located with the data, eventually the application will run much faster. So Zap scales the entire application, and so you get extreme processing of your big data to get real-time insights. Since Zap also provides us with cluster information about statistics, what's going on in the cluster, management, monitoring, metrics that we want to provide both to the system administrators and the marketing, this has also already been said for us. And another thing that, of course, is very important to each organization is that Zap ensures high availability. The way Zap ensures high availability is by, like we said before, provides primary partitions and backup partitions. Of course, that in each application it differs. You can define how many backup partitions you want. These backup partitions are basically synchronous. So once you write something to an in-memory data grid of Zap, so it's being written to the primary partition, but the client is waiting until it will be written also to the backup partition. So in case the primary fails, the backup takes over and the backup becomes the primary. As we said before, the database is just an asynchronous update. Of course, Zap manages redo log, and if the database is falling, Zap can continue functioning and then replay the data again and again. Same thing goes if the primary or the backup is failing. Zap can continue functioning and there is no loss of data. In addition to that, some organizations, this is usually going to the large organizations that operates multiple data centers. So Zap also provides one gateway solution that enables you to transfer the data, of course, asynchronously from one gateway to another, from Moscow to London, for example. And people are usually using that for multiple reasons. Of course, that the main reason is disaster recovery. So if the data center in Moscow is crashing, the data center in London will continue functioning and conserve the data. But some of the customers are actually using it to have lower latency time for the applications. So customers from London or from that part of the world will access the data center in London, and other customers will access the data center in Moscow. And you can define if you want that bidirectional updates or only master-slave relationship. Another solution that Zap provides is to scale the web tier. So Zap is coming with an embedded web server, Jetty or Tomcat, and then you can also store the web tier also in Zap. Another thing that you're saving there is another heat from the web tier to the application server, because once again, everything is encapsulated in the same machine. Okay? Most of the customers usually prefer to have their own web servers because it's easier to maintain and easier to scale. But sometimes customers are using Zap to store the HTTP sessions. So, and they can also, of course, replicate it from one machine to another machine. And then they leverage the in-memory capabilities of Zap to store the HTTP session. And by that, they don't need to spend time on that because customer can move from one web tier to another web tier. And also from multiple web servers and application servers. Zap, of course, since it's a distributed environment, it provides automatic scaling of the entire application, both manual and automatic. So manual is to just bring few more machines to our clusters, and then using script or using manual drag and drop to move partitions from one machine to another machine. And the automatic scaling is just to bring more machines, and then Zap will just distribute the load across themselves, across the new machines, and will make the automatic scaling. Here again, customers usually prefer to have on-demand and manual scaling, since they have more control on the application that way. So that results in real-time processing and analytics of the big data with Zap in-memory compute data grid. And this is why Zap can meet all these challenges for us. So if we go quickly over a few scenarios that Zap can solve for us, we started by scaling the data tier, and instead of storing all the data in one machine and on the disk, Zap stores them distributed and in memory. It provides us with multi-site deployment and data and disaster recovery across remote sites. It provides us with real-time processing of large event stream. Zap comes with plugins for Kafka, for Storm, and for other tools that provide us with large event streaming. Real-time queries and analysis of large data sets. Zap comes with very complex query mechanism and also aggregation, nested queries. We are going to see some examples. Online transaction processing. Zap, as opposed to other distributed environments, do provide us with full transaction supports, which is very challenging when you're working with distributed environments, because you need to lock two partitions, two shards, and to make sure that both of them got the update. And batch processing of large data sets, and scaling the web tier that we discussed also before. So another few features, we are not going to go over all of them, but just to see complex query support. Let's say, for example, that we have a person object, and we have within the person object an info object. And the info object has an address object, and that has the zip code. And I want to fetch the person that live in that zip code. So we can have a query where address.info.address.zip codes equals to something. So that's called a nested query. Aggregation supports that. We are going to see a snippet of code of that, and other complex query that Zap supports. Scala support, IPv6, extended custom security. Since Zap started mostly with the financial sector, of course that security was a base requirements, roles, privileges, authorization, authentication, everything should be supported, both for per users and also to another resolution per classes. For example, this user can access that class and perform update. The other user can perform update and read on another class. Data consistency level, optimized cross-partition update, filters for communication, scalable web UI. Of course, that's another thing that we need to make sure when we choose. Of course, that applies for every framework, but especially frameworks like in-memory data grids, is that it will be easy to manage. It will be easy to deploy a new cluster, a new processing unit, to deploy an application, to undeploy, to see what's going on in our cluster, how many reads, how many writes per second, how many transactions per second, and so on. So Zap supports that using web UI, also using a rich client UI, and using admin API that you can write scripts. Zap is available also for .NET users. So all these features, including queries, index, SQL aggregations, JMS queues, so-called, are available also for .NET. And for .NET, we also have the link provider, Change API Enhancement. So Change API is the ability to change a piece of data without really fetching it. In databases, in SQL, it's like update, but a bit more sophisticated than that. So let's say that if we have a banking solution and we want now to take an account and to add another transaction to that account, so usually what we will do is to fetch the account, to add a transaction, and then to persist the account again. So we spend time on reading the account and to sending it back to the cluster. So the Change API basically provides us the ability to send only the delta that we want to change to the cluster. So to change, to add a specific item to the transaction list of an account with the name of John Doe. Unique constraints in indexes, zone control deployment, MongoDB as external data source. So as we said before, the database goes to the back. So when the database goes to the back, so we are able to support MongoDB, Cassandra, SSD providers, and also SQL databases. Advanced projection supports. Again, in finance, usually we have POJOs with hundreds of fields sometimes. And we don't need when we want to fetch something, we don't need to fetch all the fields. So usually what we are doing is to use projection to select which fields we want to fetch. And by that, we, again, reduce the latency. And immutable object supports. More stuff is aggregation supports, custom change supports, enhanced initial load when we want to start the cluster and to fetch the data from the database. Each partition can fetch its own data, and by that, reduce the time of the initial load. Memory extend for SSD. So this is probably the killer of Zap, and we are going to discuss it soon. Query analysis, management and deployment automation, and global HTTP session sharing. This is a snippet of how the aggregation would look like. So if we have a SQL query where country equals to UK or to USA, we can get the maximum or minimum or sum or average or other aggregations that we can create. This is in Java. In .NET, it would look like that. Very similar, just using link also. Change operation that we discussed of changing the delta in the in-memory data grid would look like that. We can increment, for example, if we have a word count and we have a count field within the word count, we can increment the count by 1. If it would be the second piece of code, you can see few change operations within one query. One of them would be increment, the other one is set, and the third one is to put in map. We have also add to collection, so the change operation is very sophisticated. This is an example of a custom change operation where we have an object and we want to create a custom change. For example, let's say that we want to create a change to increase the salary by 20%. So since we don't know what the what is the current salary, we create a custom change operation. So the in-memory computing platform of Zap started with finance mostly. After finance worked so well, it continued also to healthcare, to satellite. We are working also with Frequentis in Austria, which is mission-critical applications for air satellites, online gaming, telco, and other sectors that have the need for low latency applications. Multi-site data replications is the solution of one gateway, the ability to have multiple data centers. It doesn't have to be only 2, it can be even 3, 4 data centers, and each one of them can act as a master, or so that would be multi-master, or we can have a master-slave solution. Now we can discuss some selected customers, but maybe before that we can discuss the SSD solution, which is a very good framework and this one is something that better to see with a demo. Since RAM is still a bit expensive and there is also a limit to how much we can store in memory, usually customers will not go for in-memory data grid if they want to use a cluster of multi-terabytes application. What will they do is to combine the RAM and the SSD. And the way we do it is to store the data on the SSD and the metadata and the indexes on the RAM. So when we want to fetch the data, we will fetch it from the RAM, we will run the query on the RAM, but the actual data will be taken from the SSD. And that is not using the SSD just as a fast disk, but we are using the SSD as a key value store. So this one is much, much faster than just throw our database on the SSD. By that, we can increase the cluster size from, let's say, 200 gigabytes from in-memory to dozens of terabytes using the SSD, and by that we have real-time analytics on big data using Zap, which stores the data on the SSD, but still run the calculations on the RAM. Let's see 2 selected customers, and then we can have some questions if you have. So in the industry of e-commerce, we mentioned Call before. Call is a huge e-commerce shop in the US. The challenge that they have was to handle peak loads without over-provisioning of maximum traffic, and that raised after they had the system crash in 2009 that results in loss of millions of dollars. The solution that they used is to implement the inventory management that they have on top of Zap within 4 months. So they just took Zap. You don't need to replace all of the data stores that you have in your applications. They replaced the inventory management, and they did it with Zap. It didn't take them that much time. Usually it takes more time, but Coles did it very fast in around 4 months. And eventually the result was that Coles was the North America best performing e-commerce website on Black Friday. Of course, that's after seeds. They keep improving it, and they can add more functionality and rely on Zap with other processing that they have. Avanza Bank is a very large bank in Sweden. Their challenge was to have scalable transaction processing for trading platforms. So they wanted to increase the performance and efficiency of their banking processes, and the solution was that we provided them the infrastructure, the in-memory data grid, to support all their core services, including trading, customer and data processing, and storage. So the last time I saw it, I think they had already almost 100 clusters, processing units on Zap for plenty of applications that they have. They also developed their own monitoring system on top of our monitoring system on Zap. And therefore, they have zero system cost for data storage because everything is on Zap. They have massive cost reduction because they don't need to spend money for plenty of vendors since they use mostly Zap. And they have major performance improvements since everything is being taken from the RAM, from the in-memory. That's it. You are welcome to join the booth that we have. and see the demo that we have there with some code and aggregations and see how exactly it's working. You can download Zap from our website. We have the Premium Edition and the Zap Lite Edition that supports less nodes. And that's it. I'm here if you have any questions. Questions?
Can I ask a question?
Yeah.
When would you recommend using GigaSpaces versus clustered in-memory database like VoltDB or MemSQL?
Okay, that's a great question. Usually, GigaSpaces will be used when you need much faster response, because the other databases, the other NoSQL databases, they do provide high availability and scalable solutions, but they still store some of the data on the disk. And since they store the data on the disk, it takes a bit more time. So, for example, we heard about an experience from a user that used Storm together with Cassandra. Same thing like VoltDB or MongoDB. So he used Cassandra, and using Storm, he processed all the transactions, but Cassandra was not fast enough to put all the data together on the disk, on Cassandra databases. So when you need faster response time, Zap will be probably the right solution. Another use case is when you need distributed transactions. So for example, you have accounts and you want to transfer money from one account which is on partition 2 to another account which is on partition 8. You need to lock both partitions. Most of the NoSQL databases can cope with a transaction on single node, but they don't know how to cope with transaction on multiple
I'm talking
nodes.
about systems like VoltDB or MemSQL or SAP HANA, like a real-time, full SQL real-time databases.
Sorry?
Full in-memory SQL databases. They support full SQL, including updates, clustered in memory, right?
Yeah. So then you will need to test each feature on its own. SAP HANA, for example, do not provide, and of course not to say something bad about anyone, but they do not provide a co-location of business logic and data in the same level that Zap provides. For example, FIFO grouping, messaging, batches, notifications, all of these can run, Zap can run the business logic together with the data. So this is, for example, one use case.
Thanks.
Welcome. More questions? Yeah?
What are the limitations of light version?
The limitations of light version. Okay, so first of all, the number of nodes. You cannot take a cluster of, let's say, more than, I need to check the exact number, but more than specific number of cores on the light version. So the light version is usually for very small applications. Yes, I think you can. But SSD needs its own license, but yeah, this is possible to get it. Yeah, but, and another limitation of that is the co-location. The co-location is only on the Premium Edition. Usually customers, when they start not with a co-location because that is the advanced features. So they start with storing the data on the in-memory, and then after that they continue to the co-location. More questions?